I welcome you again for this NPTEL lecture on earthquake resistant design of foundations, and this is the 6th lecture in the series. We have already covered the module 1, and in the second module, which is on the shallow foundations, we have discussed general requirements, then bearing capacity and settlement. Today we are going to talk what we call combined footings, and that is very important for earthquake loading, because if spread footing or isolated footings are not adequate, in that case we go for combined footings, which may be used even without earthquake or with earthquakes loads. So, when we talk about combined footings, the lecture will be covered under these topics. We have the introduction first, then general principles of combined footings, types of combined footings, and finally we will discuss some numerical examples. When we talk about combined footings, you may be aware that there are situations where it is better or rather economical to combine the spread footings of two individual columns, though this decision depends on the amount of the load coming, type of soil and situation, and the distance between the two columns. However, a combined footing will be perform better during earthquakes as compared to isolated or spread footings. The choice of the combined footing is preferred over to the isolated footings. So, if isolated footing is not adequate, then we go for the combined footings. As we discussed earlier, that for the as a matter of choice for the engineers, the spread footing or isolated footing should be the first choice until unless it is come out that this is not adequate. Then if spread footing or isolated footing is not enough, then we go for combined footings. When we talk about combined footings, in general it is two types. One is what we call combined footings, which is a spread footing which supports two or more columns, which is called combined footings. If distance between two columns is large, then these independent spread footings of two columns are connected by a beam or a strap, then it is called strap footings. So, when in the case of combined footing, when you do not have any beam or a strap, then combined footings is normally of two types. One is called rectangular in shape or trapezoidal in shape. Rectangular footings are normally used when both columns carry almost equal loads and there is enough space for footing, but for trapezoidal footings, if load carried by one column is comparatively larger than the second column, and then there is a requirement on the larger column, there is a restriction for the space. In that case, we do not have choice, rather we need to go for trapezoidal footing. Continue with this. General principles of combined footings are listed here. Generally it is constructed of reinforced concrete. It is assumed that footing is ridged and it rests on a homogeneous soil, and therefore it will give to linear stress distribution at the bottom of the footing. In case if the resultant of the soil pressure coincide with the resultant of the loads and CG of the footing, in that case the soil pressure is uniform below the footing, and that is this last one we follow in case of rectangular footing. So, you will see that for the soil pressure is uniform below the rectangular footing, while it is linear below the trapezoidal footing. Continue with that we are going to discuss three types. One is what rectangular combined footing, trapezoidal combined footings, and strap or cantilever footing. When we talk about rectangular combined footings, let me show you the first the figure and then we go for some calculation. Here you could see that there are two columns. In this figure you have that two columns are P1 and P2. They are having the point loads on two columns. The size of the columns are C1 and C2. So, if you distribute this load, then you get P1 by C1 on this column and on this column P2 by C2. So, this is the load which is coming from the top, and if we follow the principle that the load which is coming from the top resultant of this load coincide with the CG of the footing, then there will be uniform pressure distribution at the base, which is shown in this figure. If you draw the shear force diagram, then it looks like this, it is shown here, which have the linear variation. If we draw the bending moment diagram, then it will have the parabolic variation, and with this you can have you can find the what we call the maximum bending moment can be found. Now, what is the design principles or philosophy? The design of rectangular combined footing will consist determining the location of CG of the column loads and using a length and width dimension. So, basically what we do in the design, we find what is the length and width dimension of the footing, and they should be determined in such a way that the centroid of the footing and CG of the column loads coincide. So, on one side you have the column loads coming from the top, and when designing, if you make sure that resultant of the column loads is acting at the center of gravity of the footing, then in that case you will have the linear you will have the uniform pressure distribution as for the combined the rectangular footing is concerned. In this case, the pressure intensity for rectangular footing is simply given by this relation, where you have Q equal to P1 plus P2, P1 is the load, P1 and P2 are the loads on the two columns, and B and L are the dimension of the footing, B is the width and L is the length. Qs is here the allowable or safe bearing capacity. So, naturally the value of Q should be less than Qs. Once we know the value of Qs, P1 and P2 is known. So, this equation will give you the area of the footing, which is, so we can find from this equation simply B into L can be found out simply P1 plus P2 divided by Qs. So, the column loads are as we discussed considered as a concentrated load, and we can draw the bending moment and shear force diagram. But this equation will give you only one unknown, but we have two unknowns. So, naturally we need to use another equations which is coming from the center of gravity, and in this case that equation is simply comes that we need to make sure that in the rectangular footing that CG, let us say that if I say for this combined footing, your this resultant force, this is the CG, this is R is acting, where R will be nothing but P1 plus P2. Now, if the location of R is from this you have this is the x bar, then in that case what you have, this will be the length will be simply you have this dimension whatever, let us say C1 by 2, and then you have this A, let me put it like this. So, the L will be 2 times of A plus x bar. So, the length can be found making sure that the resultant of the loads coincide with the CG of the footing. So, this is a resultant of load coincides with CG of the footing. So, with this we can find the value of L. Once L is known, then you, because area is known, so B can be simply found area of the footing divided by L. So, this was about rectangular footing. Now, when we talk about trapezoidal combined footing, when the two columns are unequal with the outer column coming heavier load, and when there is a space limitation beyond the outer column, a trapezoidal combined footing need to be provided. There are so many restrictions. First of all, the load carried by the columns are not equal, and the outer column where you do not have much space like is shown in this slide. Let us say this is you have two columns P1 and P2 are the load carried by this. So, you see that there is a space limitation on the outer column. So, you cannot extend this outer column beyond this edge. So, that is the restriction, and if this column is carrying heavier load, then we may not be able to have the rectangular footing for this, because for the rectangular footing you need to have that center of gravity of the footing should coincide where the resultant force is acting. So, and if we try to do that, then the footing will extend beyond this column load. So, that is the restriction. So, here the situation is like this: the column C1 is carrying heavier load and there is a limitation that we cannot extend the footing beyond the edge of this column. So, in this case you do not have a choice, rather we go for trapezoidal combined footing, and in case of trapezoidal combined footing the plan of the footing is shown here, footing plan, which have the dimension more under heavier load. That means B is greater than A. In this case they are not equal, B is greater than A, while for rectangular footing B was equal to A, that means both the size these were the same. So, in this condition once you have B is greater than A, we provide this rectangular footing, trapezoidal footing, and then once you have the other things are remain same, that means still we need to make sure that the resultant of footing loads plus this footing coincide with the center of gravity of the. So, you have the P1 and P2 loads coming from the top and the resultant should coincide with the CG of this trapezoidal footings. So, that we will make here what we have continue with in the case of what we have discussed for the rectangular footing, the total area of footing will be now A plus B by 2 into L, earlier it was simply B into L. So, A plus B by 2 into L, and this total area will be as before P1 plus P2 divided by QS. So, now you see that this equation give you the value of A plus B, that is the sum of A plus B, but and provided in this equation you already know the value of L. Here the value of L is fixed from other considerations like the eccentricity consideration, other consideration. So, it is already from practical consideration it will be assumed that the length of footing is known to us from other consideration. Then we have one equation A plus B which is given using equation number 1, but again there are two unknowns A and B. To find A and B we use another equation which comes from the that the resultant should coincide with the CG of the footing. So, that equation is developed here. Let us say the CG of the footing is at this dotted line, and at this dotted line is the point where the resultant force R acts on this case here. So, what you have on this CG, this is actually this is continue here exactly on this line, okay, this is little anyway. So, you have this, the total load P1 plus P2 will be the R will be nothing but P1 plus P2, and when you have this load total load, this is acting at the CG. If CG is at a distance, let us assume x bar from the center of the column 1, then what we can have, we can take the moments of all the forces about the column 1, then what you have P1 plus P2 into x bar equal to P2 into L1. So, using this relation we can find the value of x bar, which is x bar is the distance shown in this figure, and then x bar will be this x prime is shown here, x bar is will be the C1 by 2, where C1 is the width of the column plus this distance. So, this and this x bar should be equal to the centroid. In the trapezoidal case, or for a trapezoidal case, this is the centroid given L by 3 2a plus b by a plus b. So, using this equation we can have the value of another equation where 2a plus b and this second equation. Right hand side is known provided you know the value of L. L1 is already known, L1 is nothing but the distance between two columns, center to center distance. So, this second equation is also available, and simultaneous solution of this equation and equation number 1 will give you the value of A and B. Once you know the value of A and B, then you can determine the loads carried by the individual footings, that is the intensity which is shown in this figure. The value of Q1 you could see in this stress distribution and Q2 at this A's. So, the value of Q1 will be simply B into Qs and Q2 will be A into S. So, once you know the value of B and A, then we can find the pressure intensity below both the footings. And once this stress distribution is known, bending moment and shear force can be drawn, and again we find the maximum bending moment, and that maximum bending moment is used in structural design of the footing. It is important to note that for a rectangular combined footing x bar was L by 2, while for if you have a triangular footing, that means when I put the value of A equal to 0 and if you have B only, then this will becomes a triangular footing, and for triangular footing x bar will be L by 3. So, trapezoidal footing will be have a solution that x bar should be greater than L by 3 and it should be less by L by 2. So, this check need to be applied when we design a trapezoidal footing, that the value of x bar lies in this range. So, this was about trapezoidal footing. Continue with that. Now, we have the third one, that is called strap or cantilever footing, and this footing can be used where the distance between the columns is so large that a combined trapezoidal footing will be narrow, and if it is the like if because in the combined trapezoidal footing you have the continuous footing, and its what will happen, its length is large and then its width will reduce and you will have the high bending moments, and that is not going to be economical because whatever you provide. Or in case trapezoidal solution is coming where x bar is coming less than L by 3, then in that case we are not able to provide the trapezoidal footing. So, a strap footing is provided. In case of a strap footing, it consists of a strap footing of 2 columns, they are connected by a strap beam which is shown here, like you have this strap footing, there are 2 columns here. It is similar what we have seen in the trapezoidal footing. Again there is a limitation on the outer column, that on the outer column you may not be like that able to provide the space beyond this. So, with this limitation we can try for this case trapezoidal footing, but because the distance L between 2 columns is large. So, as a result you will get a very long length of combined footing and that footing may not be economical. So, what is done? We provide in case of strap footing, footings, individual footings under 2 columns which you can see here, that this is like this is the first part here and then you have the another footing here, these 2 individual footings, and rather than combining these 2 footings continuously, a strap beam, this is called strap. So, you have this strap is provided, and under this strap, once you have this strap connects 2 footings, but one thing need to be noticed, that this strap is not in contact with the soil. So, the objective of this strap or beam is to transfer the load from one footing to another footing, not directly to the soil, because this is not in contact with the soil. So, strap itself will not transfer any load directly to the ground or soil, rather it is acting like a beam which transfer load from one end to another end depending on that. So, and we can design, and it has been found that using this strap is more economical compared to combining the footings of these 2 columns. So, this was like that. So, so already we have discussed that this strap is assumed to be infinitely stiff. It serves to transfer the column load onto, it does not transfer the column load on the soil directly, but it transfer from one end to another end. Now, talking about that, how the solution, like you could see that if let us say P1 and P2 are the loads coming on the column 1 and column 2, and R1 and R2 will be the reaction. Now, the reaction is not combined because you have 2 separate footings. R1 and R2 will act at the center of the footings, while P1 and P2 are acting at the center of the columns. If we see here, the second column have the symmetrical footings, that means the footing is like the column is situated at the center of the footing. So, in that case the centroid of this footing coincide with the center of this axis of the column. That means, the load P2 and reaction R2 are passing through the same line, there is no eccentricity. However, this is not possible for the case for the first column. If you see in the first column, the footing is larger and you have a restriction of space on the outer edge. You cannot extend the footing of the outer edge beyond this. In this case, the reaction of the footing R1 is acting at the center, while this column load is acting at the center of the column. So, the distance between the center of the column and the center is called the eccentricity E. So, this is, that means this is eccentric footing, and this eccentricity is important. This eccentricity E can be decided from practical consideration, and once we fix the value of E from practical consideration, then we can design the footing the first footing as well as the second footing. Now, let us talking about that. What we do here, that similar to last like for the trapezoidal footing, we take the moments of all the forces about the center of the column 1. So, what you have here sorry, center about the column 2. So, because these will be cancelled out. So, you take moment about P2. When we take the moment about P2, so you have R1 into this distance L prime should be equal to P1 into L. L is known to you because L is the center to center distance between two columns, while L prime L dash can be known if you fix the eccentricity, which will be simply L minus E, the distance between these. So, this will be, so once eccentricity is fixed, then L is prime is also known. Now, the total load P1 plus P2 will raise the reaction R1 plus R2. Once you have this R1 plus R2, that means, and using this relation you get the value of R1. Once R1 is known, then R2 can be simply found the total load P1 plus P2 minus R1. So, this reactions, both reactions R1 and R2 are known. Now, the next step is to get the value of total the length L1. L1 for the first footing can be simply found C1 by 2 plus E, and this is half of the total length, 2 times of this will give the length of the footing. Now, the length of the footing, the first footing is also known, the second footing also can be just simply found from that the total load divided by the area. If B is the width of the footing for the first footing, then B can be found total load R1 divided by L1, the length, divided by QS. L1 is already known, QS is already known. So, using this relation we can find the value of B, and if we substitute in this relation all this other, so this can be also written QS into B into L1, and then this will be the reaction R1 P1 into L. So, R1 L minus E. So, this equation, using this equation you can also get the value of directly from this equation you can get the value of L1, you can get the value of this B from this equation. So, because L1 is already found out. So, this equation will give the value of B. So, once you know the B and L1, that means design of the footing is completed. So, this completes all the 3 types of footing. Now, let us discuss some numerical examples one by one on each footings. So, the first numerical example is on rectangular combined footings, and this is like you have 2 columns in this example. Column 1 carry a load P1 equal to 800 kilonewton, which is shown here, and the another column P2 carried a load of 1600 kilonewton. Here you could see that there is a space limitation on the first column. That means, the footing of the first column cannot be extended beyond this edge. In this case, the load carried by the first column is smaller than the second column. So, that is why we may think about the, or the rectangular footing may be successful. But if the load would be the reverse, that means, if load carried by the first column is 1600 and the second column is 800, then the rectangular footing would not be possible in this case. So, what you have, allowable soil pressure is given to you. Once soil pressure is given, then we can find this the length and width of the footing. So, let us find the area of the footing first of all. Total resultant force 2400 kilonewton, taking the moment of the center of the column. So, x bar, what is x bar? X bar is the distance. This point you can say that, let us say this is the distance. So, this is the distance from what you have, this r is acting here. This r is the r equal to p 1 plus p 2 is acting here. So, if we track the moment of r about this the center of column first. So, r into x bar will be that p 2 into the distance between two columns. So, you have p 2 into 4.5 and x bar, r is known, p 2 is known. So, we can get the value of x bar, and x bar comes out to be 3 meter. Then because this is the center of the footing, so x bar is up to this point only, then this distance is c 1 by 2. So, this c 1 by 2 plus x bar into 2 will give you the total length of the footing. So, the total length of the footing comes out to be 2 into 3 plus 0.15. So, it comes out to 6.3 meter. So, the length of the footing is known. Now, once length is known, area of the footing is simply total load divided by the soil pressure. The total load is 2400 divided by 150. So, it comes out to be 16 meter square. Once you have total area, and the width of the footing will be simply area divided by the length. So, this comes out to be this. So, we are able to get the length of the footing as well as width of the footing, and this was the example for rectangular combined footing. Continue with that, we have this for trapezoidal combined footing. Again similar situation in the last case. Here that load is carried by the first column is larger than the second column, and there is a space limitation, and this space limitation in this case is for both columns, for column 1 and column 2 also. So, in that case once you have the restriction on both sides, then there is no choice. Even if the load would be that until unless load carried by both the columns are equal, you will not be able to provide the rectangular footing, because in rectangular footing you have you can provide when you have freeness at least on one side of the this footing to extend the footing this side or this side, but there is no choice here. So, in this case in any way we need to go for the trapezoidal footing. Yeah, if load carried by both the columns would be equal, then you could have the rectangular footing. Even if I reverse the I put 1500 here and 2100 here, then still in this case you require a trapezoidal footing, because there is a restriction that your footing cannot extend beyond this side and this side, both sides. So, let us solve this example. The soil pressure given is same as before, Q as 150 kPa, total load is given, and this R will act here, it is x bar, this x prime is the distance, this is the R, this is the point, this line shows the value of R acting here, and R will be acting along this line, which is simply P 1 plus P 2, and x prime is the distance between the center and the center of the gravity, while x bar is the total from this edge to here. So, you see that what we have, let us check the solution for trapezoidal footing. Take the moment about the center of column 1. So, once you have the column 1 is this. So, it will be P 2 into this distance, P 2 into 4.6 should be the R into x prime. So, you can find the value of this x prime, simply 1500 is the load into 4.6 divided by total load. So, this comes out to 1.92. Once you know this, then x bar is simply C 1 by 2 plus x prime. So, C 1 by 2 plus x prime. So, the total x bar is this one. However, x bar should be less than L by 3. So, what we have here, if you check this here, yeah, you can find the value of x bar should be this L by 3, where L is total, L is already fixed, L is given 5 meter. So, x bar should be this greater than L by 3, and it should be less than. So, x bar is 2.12, this has been found, and this is greater than 5 by 3, 5 by 3 is 1.67. So, this is 1.67, while this sign should be greater, this should be less than 5 by 2. So, this is 2.5. So, the value, so that means both are satisfied, okay. So, that means the trapezoidal solution is possible. So, this way we have find out that trapezoidal solution is possible for this footing, and you have find the location of the center of gravity here. But still this task is not over, still we need to find the value of A and B. What is the value of A and B for the footing design, and A and B can be found with this first of all you have the total area of footing will be A plus B by 2 into L, which is L is already fixed in this case, that is 5 meter. So, A plus B by 2 into 5, but area will be total load by the soil pressure. So, area is 2100 plus 1500 150. So, it comes out to 24 meter square. So, that means if using equation number 1 and 2, A plus B comes out to be 9.6 meter, or B may be 9.6 minus A. So, this equation gives you the, but you need another equation to get the value of A and B. Another equation comes from the center of gravity. For trapezoidal footing, x bar is L by 3 to A plus B, L is already known. So, again you have A and B here, and so using this equation third and equation this, you can find using these two equations you can find the value of A and B, and once A and B are known, that means we are able to design the footing. So, this using these two solutions, two equations, the size of the footings is are known, and once that is done, then you can find the pressure distribution as we discussed earlier, that here it is not given, but Q1 will be in this case A into Qs and Q2 will be B into Qs, where Qs is already known, and the value of this pressure distribution is shown in this, like that this will be higher on this edge while less on this edge. Okay. So, now let us have a last example for which is on strap footing, that is how to have the design the strap footing. This is the similar situation which we have discussed in theory part. So, the allowable pressure is same as in the last two examples, that is 150 kilopascals. The load carried by the first footing first column is 900 kilonewton, while the second column is 1500 kilonewton. The distance is relatively large, distance given between these two is 6 meter. In earlier case it was a little less than 5 meter or 5 meter. So, what you could see, the width of both the columns are same 0.4 meter and 0.4 meter. Now, we need to design the strap footing, that means we need to find the value of L1, L2 and the width of both the footings. So, what we do, we have this first of all let us eccentricity, you could see in this figure eccentricity. So, we need to, as we discussed, that it is better that we assume the eccentricity, assuming that eccentricity of E equal to 1 meter, then simply this L prime distance between this will be L minus E, that is 5 meter. Then if you take the moments in this shown in this figure, if you take the moment about column 2, okay. So, if you take the moment, then P2 and R2 does not have any moment, and you will have P1 into L, which should be equal to R1 into L dash. So, because both P1 and R1 is not known, but L is known, L dash is known, P1 is known. So, you can get the value of R1. So, what you have R1 equal to P1 into L divided by L dash. So, the value of reaction R1 is known. Once reaction R1 is known, simply R2 will be total load P1 plus P2 minus R1, and that has been found here. So, that means you finding the moment, we are able to get the value of R1 and R2, and the length of the footing L1 can be decided if eccentricity is known. What is given eccentricity here? E. So, the length L1 will be simply E plus C1 by 2 and double of that. So, that has been found out here, 2 into E plus C1 by 2. So, you could see it is coming out 2.4 meter. Once the length is known and total reaction R1 is known, so R1 divided by Qs, this is subscript, this should be treated as subscript. So, R1 divided by Qs and will be, and then what you have divided by L1, you will give the value of B1. So, B1 is the 3 meter is the width of the footing and length is 2.4 meter, though it looks like width is more than that, but it is whatever design you are getting. So, for the first footing you have completed both length as well as width. Now, the second footing, which is symmetrical, L2 can be determined simply if either we fix the width one way that we can assume the width of this second footing same as the width of the first footing, and once width is known, then because area is known, then you can find the length of the footing. Other way we can assume that the second footing will be a square footing. In that case, the R2 will be B2 square into QS, and B2 will be R2 derive this one. So, this is automatically coming the same width as the for the first footing. So, and the width of the both footings are almost equal. So, therefore, the settlement will be also nearly equal, and there is no need to revise the design. So, this way we can find the dimension of this footing. So, this completes the numericals on combined footings. So, today we have talked about combined footing, where we have discussed about rectangular footing, trapezoidal combined footing, and then strap footings, and with all one numerical examples on in each figure. So, these combined footings should be the first choice if it is found out that isolated or spread footing is not adequate, then even for earthquake loading we go for the combined footing, and it has been observed from the damage survey earlier that the combined performance of the combined footings was better during the earthquake compared to isolated or spread footings. If combined footing is also not enough, then we go for other types of footings including raft and this D foundation. So, in the next lecture we are going to talk about raft footing or mat footing. So, that is also widely used for earthquake consideration for earthquake loads. With this I thank you very much, and we will have this one in the next lecture on raft or mat footing.